Hi everyone. In the second episode of the Advanced Locomotion Series, we'll begin by exploring the core concepts of the enhanced input system and some of its key features. Next, we'll implement the system together in C++ and create all the necessary assets. After that, we'll dive into working on the animation system. In this episode, you'll learn about a lot of stuff. We will create the AnimInstance Class in C++ and implement locomotion state machines, including jumping, strafing, and more. The enhanced input system in Unreal Engine 5 is a robust and flexible framework designed to handle input from various devices efficiently. It offers a range of advanced features that make managing input more intuitive and powerful. The system supports multiple input contexts that can be activated or deactivated dynamically, allowing for easy switching of input schemes based on game scenarios. We'll discuss an example of this when we cover input mapping contexts. Additionally, the enhanced input system includes features such as radial dead zones, chord-add actions, and various other advanced input functionalities. Let's discuss what radial dead zones and chord-add actions are. Radial dead zones are a method used in input systems, particularly for game controllers and joysticks, to handle the sensitivity and response of analog sticks. They define an area around the center of the analog stick where input is ignored or adjusted to prevent unintended or minor movements from being registered. This prevents small, unintentional movements from affecting gameplay. Radial dead zones are commonly used in games to ensure that players have precise control over their characters or actions. They help in scenarios where precise input is crucial, such as aiming in first-person shooters or controlling the speed and direction of movement. For example, consider a character that can walk forward. If every minor movement of the joystick triggers the forward animation, it would look awkward in the game and could negatively impact gameplay. By using radial dead zones, we can enhance the player experience by ensuring that the analog stick's input is both responsive and precise, reducing the likelihood of unintended actions during gameplay. Now let's quickly discuss what chord-add actions are. Chord-add actions refer to actions that are triggered by pressing multiple buttons or keys simultaneously. Chord-add actions require the player to press a combination of keys or buttons at the same time. For example, holding down a modifier key, like Shift, while pressing another key, like W, to perform a special action. A great example of chord-add actions would be fighting games. In fighting games, chord-add actions involve pressing multiple buttons simultaneously or in a specific sequence to execute complex moves or combos. Let me start by explaining the different components or the core concepts of the enhanced input system, and then we will create all the assets and set up the inputs for movement, turning, looking up, and lastly the jumping action together. There are four main concepts we need to understand to be able to use the enhanced input system. First is the input actions. Input actions are data assets which we can create in the content browser. They represent something the user can do such as firing, moving, or jumping. Input actions are the communication link between the enhanced input system and the project's code. Input actions are the conceptual equivalent to action and axis mapping names in the old system, like the jumping action and the move forward axis mapping name we created in the first episode. Input actions have a property called the value type, which determines the behavior of the input action. For instance, it can be a simple Boolean, which is ideal for jumping since it's a straightforward on or off state. The character can either jump or not. There is also a float value type. For movement, we can use the axis 2D value type, which is a 2D vector. This allows us to create a single input action for moving in all directions. In the code, we can use the Y component of this vector to move forward and the X component to move the character to the right. Next, we have the input triggers. There are 5 different triggers that represent the current state of a particular action. We can bind input actions to these states in C++, which we will do shortly. These states include started, indicates that an event has occurred and the evaluation state has begun, such as the first press of a double tap. Triggered, indicates that the action was triggered, meaning all trigger requirements have been evaluated. Completed, indicates that the evaluation process is finished. For example, in the previous episode, we bound the jump action mapping axis to the jump function using the press state and stop jumping using the release state in the legacy input system. For the release state, we could use the completed state because, at this moment, the jumping is finished. Cancelled, indicates that the player lets go of the keyboard or joystick input. These triggers help manage and respond to different phases of input actions effectively. The third core concept of the enhanced input system is the input mapping contexts. Input mapping contexts are a collection of input actions that represents a certain context that the player can be in. When we use enhanced input, we can add and remove mapping contexts at runtime for the player. A good example of using different contexts where you would want to dynamically switch between different input mapping contexts at runtime is in a game where the player can drive vehicles, fly planes, swimming, you name it. You can have multiple different input mappings, one for the normal locomotion state, one for when the player enters a vehicle, and another for when the player flies an airplane, and so on and so forth. Additionally, you can prioritize these input mappings because you might have multiple contexts mapped to the same input action. When the input action is triggered, the context with the highest priority will be considered, and the others will be ignored. This is how the input mapping context assets look. It contains a hierarchy of mappings or input actions, similar to what we did in the previous episode using the legacy input system. However, remember that this is an asset we created, which means we can create different assets for different contexts, just like we discussed earlier. First, we select the input action, for example, jumping. When we expand the input actions, we find a list of user inputs that trigger the action. For instance, if the player hits the spacebar on the keyboard, the jump input action is triggered, and so on. Additionally, we can apply different modifiers to the raw input from the user device to determine how an input's raw value is filtered or processed. We will add mapping contexts to the player in C++ in a moment. Mapping contexts are added to the local player. Each player that is active on the current client or listen server has a local player. Finally, we have input modifiers, which are preprocessors that alter the raw input values received by Unreal Engine before passing them on to input triggers. There are multiple input modifiers we can use, such as negate, which simply inverts the raw input value. We will also use the swizzle input axis values for directional input like movement to make certain keys register as y-axis instead of the default x-axis. Before we begin implementing the enhanced input system and creating the necessary assets, I highly recommend reading the Unreal Engine documentation page on the enhanced input system. Many of the details I've explained are from there, but I've omitted a few aspects that we won't need here. Now let's open our project in Unreal Engine and get started. The enhanced input system is enabled by default, so we can create input assets directly from the content browser. In the content browser, create a new folder to store all the actions and mapping context assets and rename it Input. Before we begin creating the input action assets, let's review the inputs we added in the previous episode using the legacy input system in the project settings to identify which input actions we need to create assets for. We will need action assets for jump, move, which will handle all directions using the axis 2D, and look, to manage both turning and looking up. In the input folder we created, right-click, select the input category, then select input action. The naming convention is IA_ followed by the action name. Let's start with the jumping action. Open the asset and set the value type to Boolean, which is the default, so we don't need to change anything. Simply close this asset for now. Create two additional assets, one for move and one for look. For the move and look action assets, set the value type to axis 2D. Finally, create the input mapping context. The naming convention is IMC_ followed by the input mapping context name. Let's call it default. Open the asset and dock it up here. Let's quickly start by adding the jump action. Select the jump input you want. I will bind the spacebar for jumping. You can also add a gamepad input binding. This is similar to what we did in the previous episode. Next, let's add the move action. We will start by binding the WSD keys for directional movement, and we'll add gamepad bindings later. By default, the axis is the x-axis, which represents right and left movement. Therefore, we need to use the swizzle modifier to register the W and S keys as y-axis inputs instead of the default x-axis. For backward movement, we'll choose the S key, register it as y-axis, and negate it to indicate moving backward. The D key will be for moving right, and the A key for moving left. Since the x-axis is the default x-axis, we only need to negate this key. For gamepad bindings, we can use the gamepad left thumbstick 2D axis. For the gamepad, we can also add a special modifier like the radial dead zone, which we discussed earlier. Finally, let's add the look action. For mouse controls, we can use the mouse 2D axis, representing both turning and looking up. We will separate the X and Y axes in the code. To invert the Y-axis, or basically the lookup state, we can use the negate modifier and restrict it to only the Y-axis. For the gamepad, we can use the gamepad right thumbstick 2D axis and also add the radial dead zone modifier. Now let's jump to the code to hook up the whole input system. In the main character.h file, within the private section, let's create references to the input mapping context asset we created, as well as references to the input actions, jump, move, and look. Since we need to set these references in the editor, which we will do shortly, we will mark them as edit anywhere. Visual Studio displays an error because it doesn't recognize these classes. Similar to how we handled the spring arm and the camera component, we will forward declare them. This only needs to be done once, and any subsequent variables using the same class that has already been forward declared will be recognized by Visual Studio. Let's review the functions we've created previously. For example, the move forward function takes a float parameter to indicate if the player intends to move forward or backward. However, with the enhanced input system, this approach no longer works. Remember when we created the move action assets, we set the value type to axis 2D, allowing us to access all directional inputs. Therefore, instead of having separate functions for forward and right movement, we only need one function. Let's remove these functions and create a new one called move. This function will take a special struct parameter called fInputActionValue. This struct has a templated function called get, which allows us to fetch the vector 2D values that we can use for directional movement. Again, Visual Studio displays an error because it doesn't recognize this struct, so let's forward declare it at the top. The same applies to the turning and looking up. We no longer need two separate functions. So let's apply the same changes to the look action as well. Let's have Visual Studio create the definitions for both functions. Then head to the main character.cpp file to start writing the movement and look code. We won't write anything new. We'll just modify the way the input is handled, using the same logic from the previous episode. For the move function, copy the code from one of the previous movement functions, like move forward, and make some adjustments. Let's quickly review the logic as we modifying the functions. First, we check if the controller exists. Then we check if there's any input from the user. Since the value parameter is no longer a simple float, we will remove it from the if statement. We'll use the templated get function to access the input. Since we need an axis, fvector2d will work. Call the get function on the value parameter to retrieve the input from the user. We get an error because we need to include all the headers that were forward declared in the main character.h file. I have these header files in my notes, so I'll copy them here. I got these headers from the Unreal Engine C++ documentation, as I showed you in the previous episode. Great, now the error is gone. The movement logic remains unchanged. We get the rotation of the controller and then calculate the forward direction based on it. Since this function now handles all directional movement, we should also calculate the right direction. Or simply we can copy it from the moveRight function we created previously. The only error we should see now is related to the value parameter. For the forward direction, change the value to movementVector.y, representing the forward and backward values from the user. For the right direction, we can use movementVector.x. Now delete the move forward and move right functions, as we no longer need them. In the look function, we will do something similar. Let's start by retrieving the input and storing it in a 2D vector. Then we check if the controller exists. We use the look vector values to call add controller input and pass in the X component. This represents the turning state. And add controller pitch input and pass in the Y component. This represents the looking up state. Finally, let's remove the turn and look functions. Now we still have two things to do: adding the default mapping context we created to the player and binding the input actions. To add the default mapping context to the player, we can do this either in the begin play method or in the setup player input component method. We'll stick the mapping context code with the bindings in the setup player input component method. Let's remove these lines since we will be using the enhanced input component instead. As I mentioned at the beginning of the video when we discussed mapping contexts, these contexts are added to the local player. Here's what we'll do. First, we get a reference to the local player. Then we create an enhanced input local player subsystem variable. This subsystem variable will allow us to add the mapping context to the player. We can obtain the local player from the player controller. If you remember, we have access to the controller through the method getController. This method returns an aController. We can cast it to a player controller. Player controllers are used by human players to control pawns. Next, we create the enhanced input local player subsystem variable. The uLocalPlayer class has a public and static templated method called getSubsystem, to which we pass the local player. Finally, we call the addMappingContext method, passing in the default mapping context reference variable we created. The second parameter, which asks for the priority, will be set to 0 for now since we only have one mapping context. To set up the action bindings, we need an enhanced input component, which we can get by casting the player input component. This component is responsible for handling input in the enhanced input system. Let's start by adding the jump action. Similar to what we did in the previous episode, we call the bind action method on the enhanced input component. The first parameter requires the jump action asset itself, for which we have created a reference. Next, we specify the trigger state. Recall that we have multiple states such as started, completed, etc. We can specify the trigger state using the eTrigger event enum. In this case, when the player presses the input, we set the trigger to started, indicating the jump should occur immediately. The third parameter requires the object that owns the function to be bound, and since all the functions we created are member functions of this class, we pass in this, which refers to the current instance of the main character class. Finally, we specify the address of the jump function. Duplicate this line, change the trigger state to completed, and update the function name to stop jumping. This will occur in the release state, or when the jump is finished. This is similar to the previous episode. To bind the move and look input actions, we follow the same process. We call the bind action function, passing in the move or look input actions. The difference here is in the trigger state, which we set to trigger the action once the input is detected. You might wonder why we aren't using the bind axis function here. In the enhanced input system, bind action is used to handle various types of input actions, including complex and contextual inputs. It is preferred over bind axis in this context. For example, setting the trigger state to triggered for the move and look input actions means the function will be called when the action is triggered, allowing it to handle complex inputs more effectively than a simple axis binding. Now we can remove all the input bindings of the legacy system as we no longer need them. Now save, compile, and head to the engine editor. If you face an error like this while compiling, this error happens because we mistakenly forward declaration the f-input action value struct as a class in the mainCharacter.h file. To resolve this, open the mainCharacter.h file and change the class keyword to struct. This should eliminate the compilation errors. Once the editor has launched, open the main character blueprint asset. Let's set all the references we created in C++. Since we placed all the input variables in a category named input, we can easily find them in the details panel. First, we set the default mapping context asset, and then we set all the input actions accordingly. Now compile and hit run to test it. Great, everything works as expected. Now let's begin working on the animation system by starting with a simple locomotion state, which we will build upon. In the Paragon character folder, you can find the animation blueprint that comes with the character. Let's open it to see how the animation is handled. At the top, you can see the ground locomotion, named ground, because it excludes the jump state. We will create something similar shortly, but I want to show you this first to demonstrate how powerful these Paragon assets are. You can learn a lot by inspecting these assets. We'll create this asset in C++. We'll store all the necessary information in the C++ file and expose the variables and functions to Blueprint. Most of the animation work will be done in Blueprint, similar to how it's done here. Without further ado, let's start by creating the AnimInstance class. At the top, select all classes, then search for AnimInstance. Select it. Rename it to main AnimInstance or any name you prefer and click Create. As you can see, the class is currently empty. We have a couple of functions we can override to help us here. To identify which functions to use, we can open the base class we inherited from, which is UAnimInstance. By pressing Ctrl and right-clicking on the UAnimInstance class, we can navigate to its header file. Scroll down to examine the various available functions. One particularly useful function is try_get_pawn_owner, which we'll use to obtain a reference to our main character class. This function returns a pawn, but we can cast it to our main character class to access various variables and functions, such as speed and acceleration. Continuing to scroll down, you'll find two key functions that we need to override. If you're asking how I know these functions, I know these functions because I have used them before, and I read this header file. You can do the same. Try inspecting each header file you work with. This way you will learn much better. The first function is native initialize animation, which is called once when the animation instance is first initialized. This function is an excellent place to perform any setup required for our animation blueprint, such as initializing variables or setting up references. The second function is native update animation, which allows us to update animation-related properties every frame. This function is called during the animation update cycle, making it an ideal spot for handling per-frame animation logic. It's similar to the tick function in the character class. Let's now return to our main AnimInstance class and override these functions. Let's first check the access specifier under which these functions are created. They are public. I will simply copy each one of them and also add the override keyword. Now, let Visual Studio create definitions for both functions. In the native initialize animation function, we will use the try_get_pawn_owner function I showed you earlier to get the pawn owner of this class, and then cast it to our main character. In the header, let's create a reference to the main character so we can store the result of the cast. We will use this variable to access all the necessary properties. Let's also not forget to add the main character class header file. It doesn't show errors right now, but it won't compile if we don't add the header file. In the native update animation function, let's first check if we have a valid reference to the main character. If so, we can start getting references to all the necessary variables. In the header, let's create variables to store all the information we need. And we also want to expose them to the blueprint because we will need to use them to drive the transition of the different animations in the state machine in a moment. First, we need a variable to store the speed of the character. We will add a U property with visible anywhere, blueprint read only, and we will put all these variables in a category named movement. Finally, since this is a private variable, we have to add the meta specifier allow private access and set it to true. We also need to know if the character is grounded or not, so let's create a Boolean variable to store this information. We will call it b as in air. We will use the same U property specifiers. Lastly, we need a Boolean variable to store if the character is currently accelerating or not. This acceleration variable will tell us if the player is pressing input to move forward or not. We will talk about this shortly. In the CPP file, let's start by getting the velocity of the player. In this case, we only need the xy plane of the velocity vector, meaning we don't care about the vertical axis, which is the z-axis. So, we will simply set the z component of the velocity vector to 0. Then, we can use the size function to get the magnitude of the velocity, which is the speed we are looking for. Next, we will get the current acceleration of the player. There is a function on the character movement component called getCurrentAcceleration, but first, since we are going to use the movement component, we have to include its header. I already know that this header is part of the game framework, but you might have forgotten about it, so you can search for it in the C++ documentation just as we did in the previous episode. The getCurrentAcceleration function returns the current acceleration of the character as a vector, which is the rate of change of the character's velocity. Acceleration is the change in velocity over time and can be affected by various factors such as user input, gravity, and other forces. We will simply use the magnitude of this function to determine if the player is pressing input to move forward or in any direction. Finally, we have to store the player's falling state. It's important to know if the player is currently in the air or not. On the character movement component, there is a function called isFalling. The isFalling function returns true if the character is not on the ground, like if the character is falling, jumping, or otherwise airborne, and false if the character is on the ground. Now let's compile the code and head to the editor. After the compilation succeeds, you should see the main AnimInstance class in the content browser. Open the blueprint folder, and let's create an animation blueprint based on the main AnimInstance C++ class. Search for the main AnimInstance class and select it. Rename it to BP_main AnimInstance. It shows this message because we have not selected a skeleton for this animation asset, so let's do that. Close this message, right-click on the BP_main AnimInstance blueprint asset, select Assign Skeleton, and then choose the skeleton of your character. Now open the asset and dock it at the top. We start by creating a state machine for ground locomotion. First, let's take a look at the different animation clips that come with the character. The running animations are prefixed with jog. Let's search for jog forward, which we will use as the running animation. We also have animations called jog forward start and jog forward stop, which we will use to blend between the idle and run animations. Now back to the main character animation blueprint. Right-click and search for State Machine. Let's call it Ground Locomotion. As mentioned earlier, this state machine will handle the ground animations. We will deal with the jump state later. Connect the state machine to the output pose and open it up. Right-click and create a state. The first state will represent the idle state. Duplicate it and name it Jog Start. We need another state for Jog Stop. And finally, a run state. Now let's create a transition between all the states, starting from the entry point to the idle state. Then from the idle state to the jog start. Next from the jog start to the run state. From the run state to the jog stop. Then from the jog stop back to the idle state. We also need to create a transition from jog stop to jog start and vice versa. We need these transitions because we might be playing the jog stop animations, but the player quickly pressed the moving input. If we transition to idle then we play the jog start, it won't look good in the game. So we should transition to jog start instead. The transition from jog start to jog stop is necessary because the player might press the input to move and then quickly release all the inputs, then the character should stop, instead of going for the run animation before coming to a stop. Now let's go into each state and select the animation we need to use for each one. Let's start with the idle state. In the asset browser, search for idle animations. I think this idle animation looks good. There is also another animation called idle combat. But we stick to the non-combat idle animation. Drag the animation and connect it to the output pose. For the jog start state, for now we will use the jog forward start, but later when we implement strafing we will change this to a blend space for all four directions. For the run state, for now we will use the jog forward. And finally for the jog stop, the same as the jog start, for now we will use the jog forward stop. Now we should set up the transitions between these animation states, connecting them to each other. We'll start from idle to jog start and go clockwise. To play the jog start animation, the character's speed should be greater than 0. Remember that we created a speed variable in C++ and exposed it to the blueprint. So right-click and search for it. Additionally, we need to check if the acceleration boolean is true and ensure the character is grounded. To ensure that the character is grounded, we will use the isInAir boolean variable. We can use the logical not node to negate the condition. We will use a logical and node to connect these conditions together and then connect the result to the output node. From jog start to run, this transition should happen automatically, So in the Details panel, check the flag, Automatic rule based on sequence player and state. We can also change the duration of the transition. We will set this to 0.8. This is the same value set in the blueprint coming with the Paragon character assets. You could play with this value. You don't need to use the same value. But I have played with this and tried different values and found that 0.8 is a good value. Now from the run state to the jog stop. To play the jog stop animation, the player should not be pressing the movement input, which is indicated by the acceleration Boolean variable. From jog stop to idle, this transition will be automatic, just like we did with the transition from the jog start to run. Check the flag, automatic rule based on sequence player and state, and modify the duration to something like 0.4. 0.4 is a good value. Again, you are encouraged to play with this value and see what value looks better for your character. Now from jog stop to jog start, this is simple. If the player pressed the movement input while playing the jog stop animation, then we should play the jog start immediately. Again, we can use the acceleration Boolean variable for this. And finally, from jog start to jog stop, we only want to play the jog stop if the speed of the character is 0. Otherwise, we should keep moving to the run state. Now compile, save the asset, and open the main character blueprint to set the animation blueprint for the mesh. In the Detail panel, under the Anim class section, select the BP_main Anim instance. Remember in the previous episode, we hid the gun. So let's change the material back to show the gun. You can do this in the Materials section of the Detail panel by searching for it. Wait for the shaders to finish compiling, then hit Run to test the animations. The animations are working fine, but we have some issues. You probably noticed that the character rotates with the controller. At this moment, we don't want this behavior. We only want the character to rotate towards the movement direction. Let's head back to the code and quickly fix this. We have 3 flags for pitch, yaw, and roll. We'll set those flags to false so the character won't rotate when the controller rotates. To make the character rotate towards the movement direction, we need to set the B-orient rotation to movement flag on the character movement component to true. We also need to set the rotation rate for this rotation through the frotator variable rotation rate. We only care about the yaw rotation, so set it to something like 500. You can create a float variable and expose it to the blueprint to play with the value if you want, but I'll leave it like this. Compile and head back to the editor. It doesn't seem like it worked. Sometimes when you compile the C++ code, it doesn't immediately affect the blueprint. You can try compiling again, or we can set those variables in the blueprint as well. Let's do that since it's faster. Search for Use Controller Rotation Yaw in the Details panel. As you can see, it's set to true instead of false, even though we set it to false in the constructor. Uncheck this flag. It looks like the B-orient rotation to movement flag is also not set correctly. Let's check this together. Okay, just check this flag. Now, compile and test again. This should resolve the rotation issues and make the character rotate toward the movement direction. Awesome, now everything works just fine. However, the animations don't look as expected. This is because the jog start and jog stop animations are way too long. We need to trim them down a bit. Locate these animations in the Character Animations folder and open the jog start animation. First, the character takes too many frames to begin the jog start animation. Also, it does take too many steps until the end of the animation clip. We need to make this animation way much shorter. There is no need to be this long. But to do this the right way, we can take a look at the jog forward animation clip. Let's open it up. We can see that the jog forward animation starts with the left leg and immediately. I think we only need from frame 0 up to this frame, so we can remove all the frames from the next frame to the end. We can also remove the first 10 frames or less. You can play with this until you are satisfied with the way the animation looks on your character. We should have made a copy of this animation. So if we have messed this one, we can try over. We will do this for the other animations. Okay, let's try this out. Let's do the jog stop and see if the problem is fixed. But I feel there is something wrong. We might have forgotten something. But let's do the jog stop first, then we will check the animation blueprint. Let's make a copy of this animation first. In the content folder, create a new folder and rename it Animations, in which we will put all the animations we edit. The character takes too many steps to finally stop, so we can remove all the frames from the beginning up to something like 20 frames or a little less. Something like this is a good start. Also, the animation seems to end here. We don't need more than this. We only care when the character comes to a stop. Great, let's save and give it a try. It seems that the running animation doesn't loop, so let's check this out in the animation blueprint. Yep, it is set to not loop. For the jog forward animation, we need the animation to keep playing as long as the state is active. We still have problems with jog start and jog stop. Let's open the jog start again. I will also remove these 4 frames since the character hasn't yet moved, so we don't need them. This is much better. As you can see, this takes a lot of modification to get right. Let's also open the jog stop animation. I think this animation also still a little longer than needed. We need this to be a little faster. It seems we've overlooked something. Let's review the animation blueprint to check if there are any mistakes in how we've set up the states. Okay, I see the issue. We haven't correctly assigned the edited versions of the jog forward start and jog forward stop animations. Let's update both animations and then test again. I'll rename both animations in the content browser so we can easily identify them in the blueprint. It looks like everything is working as expected now. I would make the jog stop animation a bit longer from the beginning since we might have removed too many frames initially. But now it looks good. Feel free to make a copy of the animation again and experiment with it further. Currently, when the player jumps, no animations play. Let's address that by working on the jumping animations. Open the main animation instance blueprint. Remember that our ground locomotion setup doesn't include any jumping states. To integrate jumping, we need this state machine to build the jumping state upon it, so we have to save the ground locomotion state machine. First, disconnect the ground locomotion from the output pin. Then drag from the ground locomotion pose pin and select New Save Cached Pose, renaming it to Cached Ground Locomotion. You can add a comment by pressing C while selecting it to keep things organized. Now to include jumping, we will create a new state machine and call it Locomotion, which will encompass both the ground locomotion and the jumping state. Double-click on the Locomotion state machine to open it. The first state will be the normal locomotion, which is the ground locomotion state. Open it, right-click, and select Use Cached Pose to choose Cached Ground Locomotion. Connect it to the output pin. This represents the previous state. Now we will create a new state for jumping and transition from our current ground locomotion to this jumping state only if the character is airborne. Open the transition, select the isInAir Boolean variable, and connect it to the output pin. Open the jump state to start working on the jumping animations. The Paragon assets come with multiple jump animations that we can use to create a state machine for jumping. Let's take a look at these animations. In the content browser, navigate to the animations folder of the character and search for jump. You will see multiple jump animations. First, we have the jump start, which, as the name suggests, is the beginning of the jump. Next, we have the jump apex, which represents the highest point of the jump animation before the player starts the pre-landing state. The jump land animation represents the pre-land state, where the character has landed on the ground but has not recovered yet. Finally, the jump recovery additive animation represents the state where the character has landed and is returning to the idle state. This animation clip is additive, which means we have to play it on top of the ground locomotion state machine, and we will handle this shortly. Now that we know which animations we will be using for the jumping state, let's start by creating a new state machine specifically for jumping. We'll call it Jump. We'll create 3 states, just like the animations we saw in the folder: Jump Start, Jump Apex, and Jump Preland. Let's rename the jump land state to Jump Preland, as this state is not the final landing animation. The final landing animation will be the jump recovery animation, as seen earlier. Let's open each state and select the corresponding animation. We'll set all transitions to be automatic since these animations are designed to play sequentially to form a complete jump sequence. The jump land animation is quite slow, so let's change the play rate to something like 0.2 to speed it up. Now return to the locomotion state machine. After the jump state finishes, the character will have landed on the ground but hasn't yet recovered. We'll create a new state called Jump Land to handle this situation. For the transition, we'll move to the landing state if the character is no longer in the air. Inside this transition, select the negation of the isInAir Boolean variable. Open the jump land state. As mentioned before, the jump recovery is an additive animation. First, we will find the cached ground locomotion pose. Then we will use the Apply Additive node to play the jump recovery animation on top of the cached ground locomotion pose. Set the alpha value to something like 0.65. This value represents the blend weight of the additive animation, controlling how much influence the additive animation has over the base animation. Finally, for the transition from the jump land to the ground locomotion, we will have two transitions. The first one will be automatic. This makes sense because, if the jump land animation finishes, the character should go back to idle. The second transition handles the case where the character presses the jump button while playing the recovery landing animation. In this case, we want the character to go to the jump state instead of playing the idle animation. So, we will have another transition, and inside this transition, we will select the as an air Boolean variable and connect it to the output pose. Now let's cache this state machine and rename it to cache locomotion. If you try compiling, you may encounter warning messages because when we created the transitions inside the jump state, these transitions are meant to be automatic, but it seems I forgot to check the automatic rule based on sequence player and state flag. Now back in the anim graph, we can connect the cache locomotion pose to the output pose and test to see if everything works as expected. Awesome! The ground locomotion works as it was before, and the jumping works as intended. However, I see that the transition from the ground locomotion to the jump state is a little bit slow. So let's reduce the duration to make it a little faster. I will also make this transition a little faster as well. This is much better, but the jumping velocity is a little too low. We need the character to jump a little higher. We can adjust this. Let's do this in Blueprint. Open the main character blueprint asset. In the Details panel, search for jump. There are several variables we can adjust. First, look for jump Z velocity. It's currently set to 420. Let's increase it to 500 for a higher jump. Additionally, adjust air control to something like 0.25. This determines how much lateral control the character has while in the air. Feel free to experiment with these values to find the best settings for your game. Setting these values in the blueprint, for some reason, it doesn't work. Every time I try to set the jump Z velocity to 500, it changes to 50,000. So instead, let's set these in the constructor in C++. Open Visual Studio. In the main character.cpp file in the constructor, let's set these values. These variables are on the character movement component. Let's set the jump Z velocity to 500 and the air control to 0.25. After successful compilation, we can see that they have been set correctly. Now hit run to test this. Awesome! Now the character jumps a little higher, and also we have some control in the air. These values work for me. Feel free to modify them as you like. Let's now implement strafing. As you may know, strafing refers to the action of moving a character sideways, left or right, without changing the direction they are facing. This allows the character to move laterally while still keeping their orientation toward a specific target or direction. To enable strafing, we need a way to determine when to play the right strafe animation and when to play the left strafe animation, or blend between them. There is something called the movement yaw delta that can assist us in this process. This is a float value representing the difference between the direction the character is moving toward and the direction of the control rotation, or the direction the character is aiming or looking. Here is a simple diagram to illustrate the process. The red arrow represents the character's movement direction, and we can obtain the rotation based on this direction vector, which ranges from -180 to 180 degrees. The blue arrow represents the character's base aim rotation, usually the controller's rotation for a player-controlled character, indicating the direction the character is aiming or looking. This rotation also ranges from -180 to 180 degrees. So if we are looking forward and pressing the left input, the movement direction will be roughly -90 degrees, indicating that we should play the left strafing animation. If the character's movement direction is around 60 degrees, we should play the right strafing animation. Since we'll use a blend space for strafing, rotations like 60 degrees or -135 degrees will be blended in between, as we will see shortly. I have printed the movement yaw delta on the screen to demonstrate how we can utilize this value. If I don't press any input, the value will be 0. which makes sense because the character's velocity will be 0. If I look forward and move forward, the difference is also 0. However, when I try to move sideways, you can clearly see that positive values indicate that we should play the strafe right animations, while negative values indicate that we should play the strafe left animations. So, regardless of the controller rotation, we always consider the difference because we want to play the animation based on the character's movement input. But now the character rotates toward the movement direction. Since we need to implement strafing, the character should no longer rotate toward the movement direction. Instead, the character should run forward, run backward, strafe right, and strafe left. By using a blend space, we can also achieve a smooth blend between the different animations as we will see shortly. Remember that we previously set the BU's controller rotation yaw flag to false. Now we need to set it back to true, which means the character will rotate based on the controller's rotation. We only care about the yaw rotation, so we'll leave the pitch and roll set to false. Additionally, we need to set the B orient rotation to movement flag to false, as we don't want the player to rotate toward the movement direction. Open the main character.cpp file. In the constructor, set the BU's controller rotation yaw flag to true and the B orient rotation to movement flag to false. After a successful compilation, open the BP_main character blueprint asset to check if the variables are set correctly. If they are not set, try compiling the code from Visual Studio and relaunching the engine. In any case, let's reset these variables in the blueprint. Alright, this is what we want. The player's yaw rotation follow the controller's yaw rotation. Currently the rotation may not look perfect, but we'll address this in future episodes by adding turn-in-place animations. For now, it's acceptable as it is. Now open the main AnimInstance class. We'll calculate the movement yaw delta value in this class and expose it to blueprint. This value is crucial for driving the animations in the BP_main AnimInstance blueprint asset. In the native update animation function, let's begin by obtaining a reference to the aim rotation, which represents the rotation of the controller. We can retrieve this rotation using the getBaseAimRotation function directly on the main character reference and store it in an frotator variable named baseAimRotation. Now to get the movement rotation, there is no direct way to do that. We need to calculate it ourselves. So here is what we will do. This rotation is based on the character's velocity, and the character's velocity is a vector. So we need to calculate a rotation based on this vector. The math library doesn't have a function for that, but Unreal have another math library called Kismet Math Library. Here is the C++ documentation page. Here we can find the header to include, and also we can take a look at the different functions provided in this header file. Let's copy the header file. We'll use a function called makeRotationFromX to create a rotation based on the x-axis of a given vector, which in our case will be the character's velocity. Finally, to determine the difference between two rotators, we'll use the normalized delta rotator function from the Kismet Math Library. This function subtracts one rotator, B, from another, A, where it represents the movement rotation and B the base aim rotation. While this function returns an F rotator, our focus is solely on the yaw rotation. With this calculation completed, let's create a variable to store this result and make it accessible to Blueprint. It's a float variable, and we will call it movement yaw delta. We will use the same U property we used previously. Now compile and head back to the editor. Let's see what strafe animations come with the Paragon character asset. Search for a jog right. This is the strafe right. Let's create a new folder named Blend Spaces within the Animations folder to organize all the blend spaces we'll be creating. Right-click in the Animations folder, select Animation, and then choose Blend Space. Rename it to Running Blend Space, since this blend space will include forward, backward, and strafe animations. In the Asset Details panel of the Running Blend Space asset. For now, let's configure the horizontal axis, the vertical one we will visit in the future. We'll name it yaw delta, and this axis will represent the calculated movement yaw delta that we just computed. As noted earlier, the range for this value spans from -180 degrees to 180 degrees. The smoothing time variable is used to control the interpolation time when blending between different animation states. This will ensure that transitions between animations are smooth by interpolating between the current and target animation states over a specified period. We can set it to something like 1.5. You can definitely play with this value. In the asset browser, let's search for the different animations we want to use. Let's start with the jog forward. We will play this animation if the yaw delta is 0 because 0 means the player is facing forward. However, if the value of the yaw delta is 90 degrees, we will play the strafe right animation. In the asset browser, it's called jog right. -90 degrees means left strafing. Again, in the asset browser, it's called jog left. And finally, for the -180 degrees and 180 degrees, which means that the character is moving backward, we can play the backward animation. Observe the blending as I move between the animations. Now save the asset and open the BP_main AnimInstance blueprint asset to set this blend space. In the anim graph, open the ground locomotion state, and in the running state, remove the jog forward animation. We don't need it since we already included it within the running blend space. Drag the running blend space from the asset browser and connect it to the output pin. For the yaw delta, right-click and search for the movement yaw delta variable we created in the main AnimInstance class. Let's hit run to test it. Awesome! Now we can move forward, backward, strafe right, and left, and smoothly blend between these animations. You can even try diagonal movements to see how they blend. However, this isn't the final result we're aiming for. Don't worry, we'll address and refine these issues as we progress further. The clipping issue with the legs during diagonal movement occurs because of the blending between forward or backward and strafing animations. We'll address this issue in a future episode when we implement hip turning. For now, we'll leave it as is. Finally, we will add directional jog start and directional jog stop blend spaces. The Paragon character comes with the jog start and jog stop animations in all directions. Let's check them out together. In the character's animations folder, search for a jog right start. This animation is the start animation for the strafe right animation. Let's create a new blend space called jog start blend space. Select your character's skeleton and open it. Dock the asset at the top in the main window. To determine which animation to play based on direction, we can use the same yaw delta value ranging from -180 degrees to 180 degrees. We'll set the smoothing time to approximately 1.2 seconds. For now, let's add these animations as they are, but we'll revisit them later because these animations are too long, so they may not look good in the game. Just as we did with the running blend space, we can search for each animation clip in the asset browser. All animations are prefixed with jog, followed by the direction and start. Let's start by adding the jog forward start. Place the jog forward start animation at the center of the blend space, corresponding to the yaw delta of 0 degrees. Set the jog right start animation at 90 degrees on the horizontal axis of the blend space. Position the jog left start animation at -90 degrees on the horizontal axis. And finally, place the jog backward start animation at -180 degrees and 180 degrees on the horizontal axis. Now open the BP_main AnimInstance blueprint. In the jog start state, remove the single animation and instead add the jog start blend space. We will use the same movement yaw delta value for this blend space. Additionally, let's ensure that this blend space is set not to loop. We will uncheck the loop flag in the details panel to achieve this. Let's compile and give it a try. Okay, it works. The animation blend space works just fine, but the animations need some adjustments. In the jog start blend space, let's replace the jog start with the jog start edited, which is the one we edited previously. For the right and left jog start animations, we will copy the original ones and trim them down since they are too long. That's why they look bad in the game. Let's search for a jog right start animation and copy it to our animations folder to edit it. The easiest way to edit this is by opening the jog right animation and observing how it starts, particularly noting which leg moves forward first. I noticed that the left leg is almost on the ground, while the right leg is in the air. Let's adjust the jog right start animation to match this initial pose. I'll remove the first couple of frames from the animation because the movement hasn't yet begun. Leaving these frames in could lead to foot sliding issues during animation playback. Okay, I think this is enough. I will remove all the frames from 15 to the end of the animation. I encourage you to play with this. Let's now update the jog start blend space. We will do the same thing with the jog left start. I will find the animation, copy it, and edit it the same way. Let's give it a test and see how things look after trimming the animations. There is some sort of glitch in clipping. This issue happens because of the slow transition from the jog start state to the run state. Let's reduce the duration of the transition to make it quicker. Something like 0.2 is a good value. Awesome. Now everything looks good. There are a couple of settings on the character movement component we can play with to fine-tune the move to stop behavior. Those variables are the ground friction and the braking deceleration walking. These settings affect how quickly the character comes to a stop when movement input is released. Open the BP_main character blueprint asset in the details panel, search for character movement, and scroll down to the walking section. We will set the ground friction to something less, like 2 for example. This variable controls the amount of friction applied to the character when it is in contact with the ground. Low ground friction will cause the character to take longer to start and stop moving, which can give a sense of momentum or slipperiness. This is the effect we want when the stop animations play. The character is coming to a stop, not stopping immediately. The other variable that will help with this is the braking deceleration walking. Let's decrease it to something like 100. Now let's test this in the game and see the results so far. Awesome. This looks much better, but we still have the jog stop blend space to add for everything to look even better. So let's now start working on the jog stop blend space. We'll follow similar steps as we did for the jog start blend space. To keep things organized, I will quickly create two folders to store the jog start and jog stop animations separately. I'm going to quickly add the word edited to the end of all animations so they're easier to identify in the blend space asset within the asset browser. Let's now create the jog stop blend space. Rename it jog stop blend space and open it up. We will use the same yaw delta value. In the asset browser, search for the jog forward stop edited. Remember that we edited this animation previously, so let's add the edited version from the beginning. Let's also add all animations that we've postfixed with edited, even if we haven't edited them yet. We'll update them soon. In the BP_main AnimInstance, double-click on the jog stop state and add the jog stop blend space instead of the previous single animation. For the yaw delta, we can't just use the movement yaw delta again. When it comes to stopping animations, once the player releases the input, the character's velocity will drop to 0, which means all the calculations will yield to always play the forward stop animation, and we obviously don't want that. Let me first show you the problem and then we will fix it. Don't forget to uncheck the loop option as well. As you can see, I moved to the right, and when I released the input, the jog right stop animation should have been played, but the forward one played instead. So what we will do to fix this is we need to save the last frame of the movement yaw delta value. So even if the player let go of the input, we would still have the correct value. In the main AnimInstance class, we will first perform a simple check to see if the character's speed is greater than 0. Then we will save the movement yaw delta. This is necessary because we need to capture the last frame when the character stops moving. Remember that when the character stops moving, the movement yaw delta will be 0. We will save this last frame in a variable, which we can call last movement yaw delta. This variable will hold the last frame of the movement yaw delta, as it only changes when the player is moving and remains constant otherwise. After successful compilation, change the movement yaw delta to the last movement yaw delta. If the last movement yaw delta variable doesn't show in the blueprint, which happens frequently, the best way to fix this is to close the editor, compile the code from Visual Studio, and then relaunch the engine from within Visual Studio. Once I compiled the code from Visual Studio and relaunched the engine, I could see the value. Now connect it and hit run to see the results so far. Great. Now everything looks much better. The only thing left is to modify the animations. Just like we did with the jog start animations, we will start with the right one first. Find the jog right animation clip. We want to see how this clip finishes so we can match the jog right stop animation with it. By the way, I open the asset by clicking on it while pressing the Shift key. This way we can open two animation assets at the same time. If you want to ensure that a particular asset always opens in the main bar at the top, if I recall correctly, we can adjust this in the Preferences settings. To do this, open the Preferences window from the Edit menu. Locate the Asset Editor Open location and set it to open in the main window. Let's confirm that it worked. Let's try to open the BP_main character blueprint asset. Okay, I think it worked. Let's now go back to the jog right stop animation and trim it. I will speed up the video now because this takes quite a lot of time to edit, and I already showed you how to fix these animations. The right jog stop looks good. We can try to trim it down a little further to make it a little quicker. Awesome. This is much better. Now let's quickly fix the left one, following the same steps with the jog right stop animation. Awesome. This is exactly the result we want, though we could trim the jog left stop animation even more from the beginning, but I leave that to you. That will be it for this episode. We learned about a lot of stuff, and I hope that you learned something new and have enjoyed this episode. Thank you for watching, and see you in the next episode.